Hello everyone. This session is on creating design surfaces for WisDOT earthwork quantities. Calculating earthwork is a wide-ranging topic. The complexities can vary quite a bit from project to project. This class will explore some of the ways to create these subsurfaces or surfaces below subgrade, or as we call it, datum surface, that are needed to calculate earthwork quantities. These are the surfaces of materials that are accounted for in addition to common excavation. The surfaces I will be covering include subgrade improvement, excavation below subgrade, otherwise known as EBS, marsh, and rock. You may or may not encounter some of these materials on a regular basis, but it's good to know some of the options that you have for creating these materials in Civil 3D. I'll also be reviewing on how to review these materials after they are calculated in Civil 3D. Even though many of the calculations occur behind the scenes, it's still a good idea to have a solid understanding on calculating earthwork and reviewing the data. In the Wisconsin Department of Transportation standard specifications, earthwork is broken down into 4 different classifications. In section 205, there is common excavation, which includes EBS, rock excavation, which also includes EBS, stone piles and stone fences that we won't be covering today, and marsh material. In Civil 3D, we have taken these materials into account to create our quantity takeoff criteria named WisDOT Mass Ordinate. The existing surface is the current topography of the Earth's surface. This is usually collected through aerial collection methods or field survey or a combination of the two. Additional information on creating these surfaces can be found on our Civil 3D knowledge base for more information on that. The next one is rock. This surface defines the top of the rock surface. How the existing rock surface is created can vary depending on the information that's available to create the rock surface. There's a few different options or methods that could be used. Either the rock is created from boring data or probes if it's shallow enough to collect that information. Other options could include offsetting the existing surface based on boring information, or you may have a rock surface supplied by a geotechnical company that may provide a surface or additional information that you could use. And finally, marsh bottom. This surface defines the maximum marsh depth that will be excavated. It may not be the physical depth of the existing marsh material, but it'll be the depth to which the excavation will go down to. There are also a few options for creating an existing marsh surface as well, similar to how the rock one was created. It could be through marsh probe information or boring data as well, and then creating a surface from there. It's just good to note that the final marsh bottom surface is used to define the area of marsh that will be excavated. And everything from the existing surface down to this marsh bottom is considered marsh material in Civil 3D calculations. For the design surfaces, the first one we have is the datum surface. This is the surface below the pavement structure, and then from the subgrade shoulder point follows the top surface of the proposed cross-section. We have a lot of information on how to develop this on our Civil 3D knowledge base, and you can go there for more information to learn more about that. Kind of related to that is for rock excavation. This would be incorporated mainly into the datum surface. If you have rock excavation, you can have steeper side slopes, and this would be built into your datum surface outside the subgrade shoulder points. The next one is subgrade improvement limits. This is directly below the datum surface for excavating that material and replacing it with some sort of select material, say a breaker run or a combination of select and geosynthetic material. And the final two surfaces are related to marsh. The first one is the Marsh Excavation limits, the marsh that will be excavated as part of the project. And the last surface, the marsh waste limits. This defines the boundary where marsh material may be used as fill outside of the one-to-ones if that is something that is decided to be done on your project. Jumping into Civil 3D 2020, we'll take a look at our first surface, subgrade improvement. I have an assembly set up here with subgrade improvement built into it. We'll take a look at how that was put together. Under the assembly properties, under the construction tab, this assembly was made up of our WisDOT subassemblies, lane extend base, and shoulder generic. These have the functionality to create that sub-improvement layer built right into the subassembly. In the layer subassembly, there is an entry for the thickness of that subgrade improvement. Moving on to the next lane, that value can be passed along through the use of parameter reference. And what parameter reference does is it's able to read values from subassemblies that were entered prior to this one and enter those values in this subassembly. So as we can see here, I'm going to pass along that subgrade improvement thickness down to this subassembly. Same goes for shoulder generic. The thickness value has been passed along through parameter reference to the shoulder. Other functions of the shoulder regarding subgrade improvement is the width. Having a value of 0 means that the subgrade improvement will extend to the total shoulder width, meaning the sum of the paved shoulder and the gravel shoulder distance. If this value is something other than 0, then it would extend out to that actual value. Also, the closure link slope, having it 0 means it'll create a near vertical link to the datum surface. If you wanted that to be a sloping value, that could be entered here as well, and then it would slope back from the end of the subgrade improvement width. The subgrade can also extend out to the force slope. That can be done through this toggle here, either checking it yes or no. And then there's different options of how that can be created, if it'll follow the force slope, or other options as well include a user-defined value or the super elevation values. With that entered, we can take a look at the corridor. And in the corridor, we've developed a corridor surface called subgrade improvement. And that is used based on the point codes in this those subassemblies generated these feature lines for subgrade improvement along the bottom, and then the subgrade improvement intersection that goes up to the top to the datum surface, or to the datum link. And in this case, the boundary I made was to that vertical link at the top. You can take a look at that surface. Select it. And now an object viewer. You can see the bottom of the subgrade improvement and the vertical sides. The next surface we'll take a look at is EBS. There are multiple ways you could model excavation below subgrade. I'll just go over a few of them, but by no means this is the extent of how this could be modeled. Shown on the screen, you can see a construction detail that we use in our plan sometimes. It shows a line projecting from the subgrade shoulder point down to the extent of EBS, the depth of the EBS, and then back up at a 1-to-1. I will take a look in Civil 3D to see how we can construct an EBS surface, or one method. You may want to have a run-in and run-out depth, going from 0 transitioning to a full EBS depth and then back out again. To show you how I did this with this corridor, I went to our WisDOT design ribbon under our slope width control editor and created a profile using this tool, this custom WisDOT tool, and created a side slope profile. And what this does is you enter a station value and the depth. So I have my 0 at the beginning, say we're going to a depth of 4 feet, and then back out to a 0 depth. Just to show you how this works, if I wanted to add another value, say in the middle, I could do 342 for the station, add the same depth value at that location, and add it to the table. Now that it's added to the table, we'll have to update the profile. And now this will be, as you can see, now it prompts me to update my corridor. So let's take a little closer look on how this is working. If we go into the assembly, under the construction tab, the 3 subassemblies that make this possible is the profile to parameter reference, link slope and vertical deflection, and link slope to surface. The first one is a WisDOT subassembly that is able to take a profile and assign it to subassemblies downstream from that subassembly. And that is targeted in the corridor, and I can show you that once we finish here. The next one is the link slope and vertical deflection. This is the link that is created from the subgrade shoulder point down to a given depth, and that depth is achieved through the profile. We have a slope of 100% or 1-to-1. This is parameter referenced to that parameter reference subassembly. I have it selected as parameter reference elevation as slope. And I've given it the point codes of EBS to make it easier to create our surface later. And then link slope to surface finishes it off from the bottom of the EBS excavation back up to daylight. And in this case, I would leave it as cut and fill, because sometimes it may not intersect with having just cut. So we'll need both just to complete the surface. And again, the slope at 100% would be a 1-to-1 back up to the existing surface. And those are these two. The profile parameter reference is just a dot. It's hard to see sometimes. And then these are the two subassemblies. If we go into the corridor, under targets, the profile to parameter reference is targeted to that profile that I showed you initially. With that in place, the corridor is up to date. Let's take a look. And you can see the link down and the link back up. I have my surface turned off here, so let's turn that back on. And that's generated from those EBS point codes that I assigned. And we'll just give it a base course borders. There. And here's the surface that you see. So as you can see at the beginning, we're at a 0 depth. And then as we move forward, it gets deeper. carries through at that depth. Zoom in a little bit here. And here you can see where it projects past the existing. We'll take care of that in a second. Now this would fulfill what is needed for calculating our volumes. But if we want to clean up this surface, so that could be possibly used in our cross sections or used out in construction, we're going to clean this up so it just ends at the existing surface. To do that, the first thing we'll need to do is determine where the EBS surface crosses the existing surface. We can do that through a volume surface. My type will be tin volume surface. And my surface name, I'm going to name this kind of in the order of the steps that we're using here. So it'll be step 2, volume, yes, versus exist. Base core style is fine. Our base surface will be the original, or the EBS surface that we originally had. And our comparison surface will be our existing surface. So now that surface is created. Let's take a look at this in a different way. Now it's just a boundary or a border. Let's see what the contours look like. And you can kind of see here where it kind of dives in and then comes back out. Those are the differences in elevation, but we need to know where it's 0. In order to do that, we're going to have to create a 0 contour. First thing we're going to have to do is create a new style. So I'm going to copy this existing one and I'll give it a different name. Let's just call this one 0 contour. And for display, I'm going to leave the border on, and I created a layer ahead of time. We're going to call that volume boundary. And I'm going to turn these 2 contours off, and we're going to utilize these user contours. And I have a layer set up that as a volume 0 contour. Apply that, and OK. And in order to utilize that user contour, we'll go to the Analysis tab under User Contour, User Defined Contours. We just need one contour. I'm going to bring that down, and that'll be at our 0 difference between those 2 surfaces. Hit OK. And with that done, this green line now represents that intercept between the 2 surfaces. I'm going to turn some of this off to make it a little easier to work with. Turn off my corridor. Some of these here. The surface. And now we're left with that volume surface. When I select that, that's the volume surface, with those 2 representations of the boundary and the contour. Now, in order to use that downstream, I have to extract that. So we'll go to Extract Objects. And I'm going to use the border. The reason I'm using the border is, as you can see, the 0 contour, there's some gaps in here along this edge here. So I'm going to need the outer boundary to kind of clean that up or complete it. And now those go to the layer that was in the style. I can turn off that surface or make it no display. So now I just see the polylines. We want to create a boundary using this. The first thing we're going to have to do though is go to the Modify tab and Design drop down and convert this 3D polyline to a 2D polyline. Since this boundary is created by are made into a 3D polyline, it found that, accept that. So now I have polyline here and a polyline here. And I usually save at this point just in case my boundary doesn't close. Sometimes it gets hung up there. So the next step would be to type in boundary. I don't need the island detection, and pick a point. And I pick a point in the middle there. And it's analyzed that, and those are where those two, the outer extents for this infield that I've picked here. And click OK. And now that boundary is created. Now I can use that in another surface downstream for the final version. So this is my final step, step 3, and that is the final EBS sloped side. Now to fill up that, this is just an empty surface right now. So if we put information into there, we're going to utilize the, if we go to Edits, right click, Paste Surface. I'm going to paste in the original EBS surface that was generated from the corridor. That's this outer, the one in orange here. But now I'm going to trim that back using this boundary that we just created. And adding that, I'm just going to call it outer. And that is this polyline, white one. So now we've filled it with the original, trimmed it back with that boundary that we created. And we can select that. If I go to Object Viewer, slide this over, we can see that it's trimmed it. We have the one-to-one slope back up, but where that original surface extended beyond the existing, we've trimmed that back to that intercept. And now this surface is complete. Another method that we can use to create an EBS surface is by creating an offset surface from our datum surface. This is in a different location, and just for the record, these are all fictitious scenarios. None of these are actual designs. It's just for demonstration purposes of what the tool can do. So with that in mind, to create that offset surface, we use our datum surface. First of all, so we've created a datum surface from our corridor. That's step 1, the datum surface. Step 2 is to offset that surface. So I'll go through this in detail just for sake of time, but that definition is from the edits. We've pasted a surface like we did before, and then we also have the option to raise and lower the surface. If we want to lower it, we'd put in a negative number, say a -2 or something like that, and that would lower that surface. And then we have applied the boundary to that as well for that datum surface. Once we have that, we go to step 3, which is to create that volume surface like we did before. And that's to find the zero contour or that intercept between the existing surface and the EBS surface, which is our offset surface here. And then finally, once we have that intersection location between the offset datum and the existing surface, we'll paste that. We'll paste our offset datum surface from step 2 into the surface and apply that boundary, which was our 0 contour, and then that'll create that final EBS surface. If we select this surface and take a look at it, Object Viewer, you'll see the same thing here, just a flat surface, no sides, but this will work for quantity calculations and for construction purposes if needed. Another method we can use, and a final one I'll demonstrate for EBS, is utilizing a different subassembly, and this one will create vertical sides. So it's kind of a combination of the previous two methods I showed, with similar to the one with the sloping side slopes, but this one will have a vertical face on the edge of it. So let's take a look at this subassembly and see how this one is made up. In our construction tab, again, we have the profile to parameter reference, and that'll be targeted in the corridor. We've created a depth profile for that to read. And downstream from there, so this subassembly will read this profile information is our multi-use width and slope links. And this is a WisDOT subassembly that's very versatile, many times used for our setup corridors or setup surfaces, and can be used for many different things. So I encourage you to take a look at our knowledge base to learn more about this versatile subassembly. The main things in here is you can put in a width and have it follow the slopes. You can have it follow super elevation. We're going to have it daylight for the left and the right. And the other things that I've updated in this is changing the point codes to read as EBS, so then I can create my corridor surfaces, and the daylights will be daylight EBS. If I go to the corridor, we can see here that for the multi-use subassembly, we've targeted the existing, and for the profile parameter reference, we've targeted that profile we've established through our profile that we've established for the depth of the EBS. Take a look at this in Section Editor. Go back to the beginning here. You can see the EBS is at that 0 depth, but it is intersecting into our existing surface. As we proceed along the corridor, the depth starts to drop, following that profile. So we have the vertical surface if needed, or near vertical surface we'll want to create, and then that'll intercept the existing surface. It does follow super elevation. And you wouldn't technically need to include this subassembly with your design assembly. This could be run separate. They wouldn't need to be together, but it would follow the same alignment, of course. You just have to account for the depth of your pavement structure. Since right now I have the attachment point at the bottom, the attachment point would be at the top, and then you would have to account for that depth of your pavement structure and then the depth of the EBS. So I can close that. We can take a look at that surface. in our object viewer. And you can see the sides on there as well. So that's just another method. Like I said, there's other ways you could do this as well, but those are three that you can consider when developing an EBS surface. We've looked at three ways to create an EBS surface for common excavation. Next, we'll take a look at one method to account for EBS in a rock cut. In my mainline assembly, I have accounted for rock excavation beyond the subgrade shoulder point with steeper slopes for the ditches. According to the standard specifications, you should excavate the rock 6 inches below the subgrade or to the detail shown in the plan. If you added another layer to the pavement structure, that would bring the datum surface down to the bottom of the EBS surface, unless you recoded all the point codes. I've used a profile to determine the depth in my corridor. That was done through our slope width control editor. If we take a look here under the Edit tab, I've set up an EBS rock depth profile. And these values were entered in here. Next, we'll take a look at this assembly. Under the Construction tab, we have three sub-assemblies: Lane Extend Base, Profile the Parameter Reference, and the Multi-Width subassembly. The Profile the Parameter Reference will read the profile that I showed you previously. Under the Multi-Use subassembly, there is a vertical insertion point, so we could just insert this at the mainline profile and have that depth. I just added the lane extend base just as a visual representation, so if my pavement structure changed, that would account for that depth, and then I won't have to add that in addition to what I've added for the depth for the rock excavation. I've allowed the right with link to daylight, that is checked to yes, as well as the left. I've also added some point codes here for the outside, and that'll help when creating the surfaces and the boundary for the EBS surface. When we take a look at the corridor, under corridor properties, take a look at the targets. So my multi-use subassembly is actually targeting the top surface from my design corridor and not the existing surface. This is done so that when the EBS surface is below the datum surface, it'll intersect that shoulder slope interceptor, the ditch 4 slope. And we have the profile parameter reference reading our profile that we've set for the rock depth. To look through the process, as I said, the first step was to create a top surface from my design corridor. The next step was to create a rock or EBS rock surface targeting the top surface from my design corridor. From there, I combined the top surface from my roadway design and the corridor rock surface. This will create a surface from where the rock EBS surface meets the top surface. If we take a look at the edits, you can see I've pasted in, just a review from before, right click, paste those surfaces. Let's go to our design corridor to see where we're at so far. If I select the corridor and go to section editor, zoom in on our rock excavation location, so the area, since we combined the top surface with our rock EBS surface, the top surface is intersecting to the existing surface. So we need to trim that back to the rock surface for our final rock EBS surface. So the next step, like we did in other steps, was to create a volume compare surface between that combined surface and the rock surface. And that was done using a contour with elevation 0 to find where the rock and the combined surface intersect. From there, we created a boundary. Next, I created a final EBS rock surface. I created the surface. Under Edits, I pasted in our combined surface and then added the boundary from that elevation 0 contour boundary that was created. Currently I have the surface off. We'll turn that on. We'll change that to a, just for visual purposes, a base course border. And if I select that border, if I select that surface and go to our object viewer, we can take a look that now we have that combined surface for our, it has the EBS limits below our datum surface and then the side slopes in the rock excavation. Now we can use this surface as the comparison surface when computing our rock materials. The graphic shown on the screen is a construction detail that is typically used in WisDOT plans. The purple line represents the marsh surface. This establishes the depth to which the marsh excavation will take place. The green line is the limits of the marsh excavation itself for the roadway, and the red dashed line is the marsh waste limits. Beyond this one-to-one slope, EBS and marsh material may be placed in the embankment. There are a few different ways to model marsh as well. There are specific subassemblies available for modeling marsh excavation. The easiest way to review these will be to go to our Civil 3D knowledge base. You can find the help documentation for the subassemblies under WisDOT Subassembly Help. Scroll down to Subsurface, and now you can see the 3 subassemblies that are available to model marsh excavation. Marsh excavation and marsh excavation DT or design table are used on new projects, whereas partial marsh can be used on rehab projects. Let's take a look at marsh excavation. If we scroll down, we can see a graphic displaying how this subassembly works. Its attachment point is at the subgrade shoulder point. From there are input parameters to establish the slope that is projected down to the existing surface, from the existing surface to the marsh surface, and then the final parameter is the projection of a slope from the marsh back up to existing. Typically this is a 2-to-1 slope and then a vertical line and then back up at a 1/2-to-1 slope. If we scroll down, we can see some of the behavior of this subassembly as well. If the subgrade shoulder point happens to fall below the existing surface, then the vertical line is placed and the slope back up to the existing surface. We can also see the point codes that create the feature lines for our surfaces. This includes the marsh daylight and the marsh bottom point codes. The next subassembly is the marsh excavation design table. This one works a little bit differently, and you should check with your soils engineer to see which methodology they want to use for the excavation. This subassembly is attached at the end of the final daylight link. There is an input parameter to establish the distance from the slope intercept to where marsh excavation will begin. From there, it is projected from the existing surface down to the marsh surface. There are various slopes that can be used based on the varying depths of marsh. You can see here it's broken down into different ranges and the final slope of the marsh excavation that is applied. And again, the point codes for this subassembly include marsh daylight and marsh bottom. These establish the feature lines that are used in our corridor surfaces. And the last one is partial marsh. This is similar to the first one, where it is attached at the subgrade shoulder point, and then there are slope input parameters to project down to the existing surface, from the existing to the marsh, and then back up to the existing surface. This establishes the outside boundary of the partial marsh excavation. For the inside, there is an input parameter that is the offset from the baseline to the existing surface where the inside marsh intercept will begin and be projected down to the marsh surface. Again, this one has different behaviors. If the subgrade shoulder point falls below the existing surface, then it will just use the final two slope values to project from the datum surface to the marsh surface and then back up to the existing. And the point codes for creating our marsh corridor surface, our marsh daylight, and marsh bottom. To create or establish the marsh waste limits, I have inserted a link slope to surface subassembly. This is optional and does not need to be used. It is only needed if the excavated EBS or marsh material will be used outside of the one-to-one slopes. You should check with your soils engineer before applying this on the project. A surface is then created just using this one link. This surface will serve as a boundary to determine the amount of excavated EBS and marsh material that can be used as fill in the embankment. Now that we have all of our surfaces created, we are now ready to calculate our materials quantities. I have here a sample file with all the different surfaces included in it, and I've created section views to display those surfaces and the corridor. To compute the materials, we would go to the Analyze tab, Volumes of Materials, Compute Materials. We would enter an alignment and the sample line group. And now we see where we can enter those surfaces in to calculate our materials. First, let's take a look at our takeoff criteria. For WisDOT, it's named WisDOT Mass Ordinate. We'll take a look at this. And you can see the different material names on the left and the surfaces that are used to create those materials. On the right, you'll also notice that shape styles have been assigned to each material. And this will be handy when reviewing our earthwork quantities in section view. Click OK. Also notice on the right-hand side the list of materials. Our main materials of common, rock, and marsh have been broken down into a smaller materials list. This is done because many areas overlap, and we need to have those broken out so we can do calculations to come up with an accurate quantity for our earthwork. So we can fill out our surfaces, our exist surface, our datum surface, final marsh excavation limits, the material that will be removed, our final marsh bottom. This is the depth to which the marsh material will be removed. Marsh waste limits. For this case, we will be using this, and this is the material wasted outside the one-to-one slope. Our existing rock surface, EBS, and subgrade improvement. You normally won't have all these surfaces or materials on your project. This is just to demonstrate what all these would look like and the shapes that these will create. Next, we click OK. Our materials have been calculated, and now we can see these shapes within our section view. Notice the marsh excavation area, our subgrade improvement, EBS, embankment. We also have our embankment marsh waste allowable for that material that could be wasted outside the one-to-one slopes. and also our cut common. It's handy to have selection cycling turned on when evaluating this, since some of these shapes or materials will overlap. If I select on that, you can see multiple materials fall within this area. You can also see we have our rock shown in red below our rock surface. So this is handy just to make sure that everything is accounted for visually. If we wanted to see this information in tabular form, we could click on our section view, go to View Group Properties, change Volume Tables, and from here we have the option to add two different tables, a total volume table with a WisDOT style. We'll add that to our section view, and also a materials table with a WisDOT style that can be added to our section view. Since we've satisfied the criteria or entered in surfaces to calculate all these materials, we see all these materials listed. If you didn't have Marsh or EBS, you would not see these materials in this list. We'll select them all to include in the table. Next we see we can change the position of where the table is shown in our section view. I'll just leave this as is for demonstration. Say OK. And OK. And the tables show up. To clean this up, we'll update our group layout. And now for each section view, a table has been created. The total volume and also the total areas and volumes for each material. You could go into the section views and measure these areas or these shapes and see if they check out against this table. One thing to note is, just in this example, as I mentioned before, there'll be areas that overlap. As we can see here, we have an embankment subgrade improvement area that overlaps our embankment. This embankment subgrade improvement area would be subtracted from our total fill quantity, since this is already taken up by the embankment. We can also display a table for a particular material. That would be done by going up to the material volume table, picking our materials list, and then selecting the material we are interested in. Let's say we want to know the amount of excavated marsh material that could be placed outside the one-to-one slopes. I'll select that material, click OK, and then I can place my table, which will show me the total areas and volumes for this material. Once we have reviewed our materials, now we can export this information. If we go back to the Analyze tab, Volume Report, and check Display XML Report, an XML file is generated that can now be used and imported into our Excel spreadsheet for Earthwork quantities. Another check is also to review the XML file. As you can see here for sample line 1, for our cut common material, there should be 4 shapes or areas for that section view. So that would just be another spot check to see how the materials are being calculated. To see how this XML information is brought into our Earthwork spreadsheet, please refer to our knowledge base training material. So, just to review, the standard material classifications along with subgrade improvement are broken down into smaller material classifications in Civil 3D. Material areas are determined by the relation or position of different surfaces. Based on these criteria, overlaps will occur between different materials. The WisDOT Civil 3D Earthwork app then takes the material areas calculated from Civil 3D and through a series of equations determines the areas of the cut common, rock, EBS, and marsh that is exported to our Excel Earthwork spreadsheet. In the Earthwork app settings tab, there are also material ordinate equation considerations. You should consult with your soils engineer before checking these boxes that determine how excavated EBS and marsh will be used. Which boxes are checked determines which equations are used in the Excel spreadsheet to calculate the earthwork quantities. Therefore, don't copy and reuse any earthwork spreadsheet from an old project, since the use of materials may be different on your current project. Also, I would like to mention that if you're using EBS or marsh as fill, a comparison needs to be done between how much excavated marsh or EBS material there is versus how much can be used in fill on the project. And this is not an automated process. The total volume of EBS or marsh material that may be consumed or used on the project is based on the embankment marsh waste allowable material quantity. This material can be reviewed in Civil 3D, but is not imported into the WisDOT Earthwork spreadsheet. The designer will need to review the embankment marsh waste allowable material volume and compare it with the total reduced marsh infill or reduced EBS infill spreadsheet volume to see if any adjustments are needed as to where EBS or marsh can be used as embankment fill. This graphic shows the relationship of the material areas generated in Civil 3D and the calculations performed by the WisDOT Earthwork app, and then how that data is used in the Earthwork spreadsheet. There's a lot of information on this slide, so I have also included it in the handout for this class. At the time of this recording, there is also an issue that the EBS subgrade improvement material is not subtracted from the EBS quantity. Until this is resolved in our next update, EBS subgrade improvement areas will need to be subtracted manually from the EBS areas in the Excel spreadsheet. Also, please note that if you're using any surfaces besides datum and exist, that the values in the Civil 3D materials volume table will not match what is in the spreadsheet. The Civil 3D table is simply based on a quantity type of cut or fill and does not consider the overlapping areas as I mentioned earlier. That is all the information I had for today. I hope this was helpful. A handout has been provided for this class. Also, please refer to the WisDOT Civil 3D knowledge base for more information on calculating earthwork. And also, please feel free to contact me if you have any questions. Thank you for your time.